So welcome to lecture number 25 of the Statistical Thermodynamics course. So as we told in the previous lecture, that the electronic state okay, of a hydrogen atom is specified by 4 quantum numbers. Okay, the principle of this, let us see which quantum number does what. N, which is also the principal quantum number, okay, determines the electronic energy. Okay. Now, orbital L is basically the orbital angular quantum number. Okay. Designated as L. Okay. So it defines the orbital angular momentum. Okay. So this particular number is basically is totally for designating the orbital angular momentum. Okay. Now then comes ML, which is called the orbital magnetic quantum number. Magnetic quantum number. Okay. That is ML. It specifies basically the Z component, of the orbital angular momentum. Okay. And lastly, you have MS, okay, which is the Z component of the spin quantum number. Of the spin angular. Okay, so this is called the spin magnetic number. Magnetic quantum. Magnetic quantum number. Okay. So already you see that the quantum states are defined by L and ML. Now there are two possible values of the fourth quantum number. So MS has two possible values, plus and minus half. Okay. So the electronic degeneracy, therefore, for the hydrogen atom, becomes G electronic is 2 into n squared. Okay, the n is the principal quantum number. So basically, we already have seen that L and MS was the two quantum numbers that was used to generate the degeneracy. Now you add the fourth quantum number, which has got two possible values, plus minus half. So therefore, n gets multiplied by this factor 2. because of these two possibilities. Okay, so this is the four quantum numbers, therefore. N, principal quantum number, which determines electronic energy. L is the orbital angular quantum number, which designates the orbital angular momentum. Then ML is basically the orbital magnetic quantum number, which specifies in essence the Z component of the orbital angular momentum. And MS is the Z component of the spin angular momentum, also called the spin magnetic quantum number. Right? So these four quantum numbers, and MS has got two possible values. So this actually completes the total degeneracy, how to calculate the total degeneracy for the hydrogen atom. So there are four quantum numbers. Okay. And all four are basically required to designate the electronic state. And of course, obviously, the energy is dependent on the principal quantum number only. All right. So this completes this for the hydrogen atom. Now we move on to the electronic energy mode for multi-electron species. So electronic, okay, energy mode for multi-electron species. Okay. So again, for doing this, we write steady state Schrodinger wave equation, okay, for a generic n electron atom, okay, with nuclear charge Z. All right. So this is the equation that we are going to write. Nuclear charge Z at the origin. So minus h bar by 2 me summation equal to 1 to n square, okay, minus equal to 1 square equal to 1 to n, d greater than I. This entire thing is multiplied by psi. Oops, psi. Now, this first term that you see over here, first term accounts for the motion, accounts for the motion of n electrons. Okay. This is the term one. The second term, this particular term, this term accounts for hydrogen-like interaction between proton and electron. Okay. And the last term, this guy over here, okay, this particular term you see over here, the last term the third term is to account for repulsive forces. Repulsive forces among the various electrons. Making right. So these are this is the steady state Schrodinger's wave equation, which has got a charge Z at the center, at the origin. So this is the total, this is how you write the total equation form. So first one is to account for the motion, second one is to account for the proton-electron reaction, the interactions, and the third is basically to account for the repulsive forces. So this entire thing is multiplied by the wave function is equal to this. So this is the Schrodinger's steady state wave equation to begin with. Okay, so it is kind of not always easy to find out solutions to this. So there is a process called Hartree-Fock procedure. So what does this procedure actually do? So Hartree-Fock procedure, we use this procedure to basically find out accurate solutions, okay, for many atoms, okay. So it is usually done like this. So the the wave function, the total wave function is multiplied I equal to 1 to n, and this is represented by some kind of a phi. Okay, Ri. So overall wave function is a product of independent wave functions. And especially this phi I is given as summation of nij, some number j, Cij into exponential minus Ij. Okay. So this is a normalization constant. Normalization constant. These are this and this. These two are variational parameters. These two are variational parameters, okay, used to obtain the final solution. Okay. Okay, so these are also called phi I, Ri, are also called the trial wave functions. So what the solution, so this trial wave functions represent basically specific solutions to the Schrodinger's wave equation. Schrodinger equation. Okay. Or independent electrons moving in and interact in an effective potential. Trial solutions. These are specific solutions to the Schrodinger's equation or independent electrons, okay, moving in an effective potential. Find the word effective. potential. Okay, this is which is interactive in nature, basically interactive potential created by nucleus by the nuclei actually by nuclei and electrons, right? Nuclei and electrons. So final solution is obtained by iteratively guessing the values of these above new parameters and so on until you get a convergence. Okay, so you what you do is that basically you guess values and then you see that whether it converges. So it is like an iterative kind of a solution. Iterative solution. Okay, so it works very well, works well for z less than or equal to around 40. Does not work for z greater than 40. That means heavier atoms. It does not work at all. Okay, so it works, but similar calculations for larger atoms and for diatomic molecules, it does not really work that way. Okay, so therefore we can infer that Schrödinger wave equation, okay, has operational limitations. Operational limitations and cannot provide accurate electronic energies and cannot provide accurate electronic energies for atoms and molecules, or multi-electron, basically multi-electron molecules. So these are operational limitations. Okay, so you principally depend on molecular and atomic spectroscopy. Atomic and molecular spectroscopy. So each electronic level is also characterized by an associated term symbol from which we can extract the electronic degeneracy, which is required for the statistical thermodynamics, statistical mechanical calculations. Okay, so each electronic energy level, energy level is denoted by a term symbol. Okay, so which is required for the stat thermo calculations that we are going to perform later on. So we have to develop an appreciation for these term symbols, what they actually mean and how they can be used, etc., etc. Okay, so as we saw that Hartree-Fock orbital procedure can do a lot of stuff. It can give very accurate solutions, but only for smaller, more compact atoms, even for the multi-electron kind of a system. Now let us see that, we know now that there are 4 quantum numbers for the electrons of a multi-electron atom. Okay, so the quantum numbers, let's put it like that, quantum numbers for electrons, okay, of a multi-electron. Okay, so first one is n equal to n equal to 1, 2, 3, da da da. Then of course there is L equal to 0, 1, 2, da da da. n minus 1. Then there is ml, which we know ml is equal to 0 plus minus 1 plus minus 2 plus minus l. Then there is ms, which is equal to s is equal to plus minus half. So these were the 4 sets of quantum numbers. So all 4 sets of quantum numbers must specify, all these should specify a quantum state. Okay. Furthermore, say only one electron can occupy any given quantum state. This comes from Pauli's exclusion principle. Therefore, each electron of a multi-electron atom can be identified by a unique combination of this 4 quantum numbers. So there is only a unique combination of these 4 quantum numbers that can identify an electron in a multi-electron kind of an assembly. Okay, so we introduce the so-called configuration of an atom. We introduce the so-called configuration of an atom, okay, which is a convenient fashion, the number of electrons occupying each shell and subshell. That means, so this actually says the electrons, the number of electrons occupying each shell. Shell is basically n, 1, 2, etc., and then the corresponding subshell, which is basically equal to L equal to 0, 1, 2, da da da. Okay, of a multi-electron system. Electron system. Okay, the shell is specified by the numerical values. So the shell is specified by the numerical value. The numerical value of n, which is basically 1, 2, 3, etc. Okay, the subshell, which is the orbital quantum number, is specified by SPDF. Okay, corresponding to L equal to 0, 1, 2, 3. Okay. So given this nomenclature, so we have now identified that the electrons should be specified by n and then the corresponding subshell in which they are residing. Okay, so this is given in the format n, L, A. So n is the principal quantum number, which tells you the shell. L is the subshell, or SPD, and K is nothing but the number of electrons per subshell. Number of electrons per subshell. All right, so that is the configuration that we have. Okay, so n represents the shell number. Okay. As an example, if you take atomic sodium, let's say atomic sodium, for which the Z is equal to 11. Okay, the configuration for the ground electronic state will be 1s2, 2s2, 2p6, 3s. Okay, so the number of electrons, but however, you see the number of electrons per subshell is limited by okay, ml and ms, right? Okay, which is 2 into 2l plus 1, correct? So for example, when you were at s equal to 0, so there are only 2 electrons that are possible. When L is equal to 1, okay, so that means the number becomes 3. 3 into 2, 6 electrons are possible in that particular subshell, and so on and so forth. So you understand, when S means L equal to 0, so that means if you put L equal to 0 here, so the number of ways this can be counted is 2. So that's why you have the number 2. All right. Okay. And you cannot have, because if you see, L varies up to n minus 1. So when n is equal to 1, L can only be 0. L can only be 0 when n is equal to 1. Correct? So that's why we have 1s2. Okay, because there is no p. When n is equal to 2, L can be 0 and 1 respectively. That means S and P. So when it is S, when L equal to 0, this is 2. When L is equal to 1, this is actually 3 into 2, 6. Okay, similarly, you can have 3S, but then we exhaust. So it is like 2, 2, 6, 10, and 11. So this is 1 actually. That is what it is reciting. Okay, so in this configuration, in this particular way, you can basically do any kind of elements. For example, let's take the example of, Z is equal to, say, 18. Okay, is AR. Okay, so what will be the configuration over here? Okay, so first you write 1s2, then 2s2, 2p6. Out of this are common, right? Okay, this is basically common for all of these things. Okay, and then of course you write 2p6, and then what? 2p6, and then what comes after that? Then you have 3s2, and it's the same. Now you have like SPD now. Okay, so then it becomes 6 once again. So this completes the configuration of 18. Okay, so you understand, you get a good idea that how this variations is basically because of this, right? And because of this, and because of this, right? And of course, this is still the principal quantum number. So even for a multi-electron system, we can represent how the atomic configuration is. So this is how the atomic configuration is. Atomic configuration can be written in this succinct kind of a way, okay, for this, and then you can do it for any number of these things. Okay, so next class we are going to do what we call spectroscopic, okay, term symbols, okay, for multi-electron atoms. Multi-electron. It's because these symbols are very important. Some of these symbols you already know from your undergraduate, so no harm in actually seeing it one more time. Thank you.